Hello.
Hello.
Well, welcome back, folks. Looks like we can get started. I hope you all had a great break, didn't get too sick or trampled on Black Friday or anything like that. It took me a minute to realize where we were at, so we're back in section 5.3. It was a long vacation, it feels like. So we'll review what we just did on example 2 and then start going forward to the notes. We're possibly going to finish section 5.3 today, start section 6.1, but due to the pacing being a little bit slow at the start of the semester, having an actual fire alarm, we may not get too far into chapter 6. Pretty much what our goal is going to be when we go back in next week. On week 15, we're going to finish off what we were working on Tuesday, potentially taking the entirety of Tuesday to finish up our coursework. Then on Thursday of this week, we're just going to be reviewing, talking about the final exam. So we're just about there. Week 14 is a full ordinary week, but we're transitioning into review already on the very next week. Kind of strange to come back from a break and just have 2 weeks of content left to do. Then finals week. This is going to be the unusual week. There's no office hours really, but you're still welcome to schedule an appointment, write an email, those kinds of things. We won't have any class meetings whatsoever. And the registrar has placed our final exam on Friday, which is always kind of weird, but for this particular class, Tuesday, Thursday, starting at 2:30, the registrar in their infinite wisdom has decided if a Friday final makes sense. 10 p.m. to noon, 12 p.m., and it'll be in this classroom, or if you're in the online section, I'll be sending out the instructions just like I did for exams 1, 2, and 3. It's comprehensive, but it's not going to emphasize any section whatsoever. Even the new content, sections 5.1, 5.2, 5.3, and so on, and in chapter 6 work, I'm not going to emphasize those problems. They'll be equally weighted with all the rest of the content throughout the semester. It's closed notes. You can use a basic scientific calculator, although you probably noticed this is mostly a comfort. If numbers get a little bit weird, it's just nice to have something to fall back on. I try to make all my numbers pretty nice for all the exams. And as you study for the final exam, we have a couple versions, version 1, version 2. This is now the full set of notes for the entire semester. And like before, definitely have this printed out or just pulled up on an alternate tab or different screen. This is going to be the formula sheet, just like on the other exams, provided on the final exam itself. It has theorem 4, still a pretty useful workhorse theorem, the complete invertible matrix theorem, and I felt like including a lot of theorem or a lot of information on chapter 5 and chapter 6. Since that's going to be the new content, it'll be helpful to have that information there. So that's our plan so far. Any questions at all, folks, with where we're at or finals week and so on?
The final will be 10, this is 10 p.m. Will be 10 a.m. to 14?
Yeah, that's an AM right there. Thanks for mentioning that. Let me put in a quick edit. And Brian was just saying the same thing. Thanks for mentioning that, Brian. I missed the chat. So this is from 10 a.m. to 12 p.m. I'm kind of curious what the syllabus says at this point. Let me double check that. Yeah, that'd be a crazy final otherwise. Yeah, it looks like someone pointed at this out. I think this was Zarek who pointed this out way back in the day, like week 1. That was changed on the syllabus, but I never came back to change it on the Canvas webpage. So that's the accurate information there. Other questions at the moment? Okay, I'll probably be including more review stuff as we get, say, closer and closer to reviewing on this week here. So expect to see more information, more things to take a look into. Like I've mentioned, all the other exams, the best way to be really prepared for this final exam is just be fully caught up on your homework assignments. So if something's gone past due, even if it was, say, something way back in chapter 1, I'll still accept it for full credit. If you want to just take another look at those problems, maybe anything you missed, those would be good ones to review. And I'll also be posting blank exams 1, 2, and 3, so you can use those as extra, just kind of quick reviews for what could be on the final exam. But I guess that's pretty much it for the announcements. We're back in section 5.3, about to finish off eigenvalues, eigenvectors. and then we'll turn it over to chapter 6. We'll get as far as we can get with our limited amount of time on geometry of vector spaces. So here's where we left off right before going on a long week. It's kind of a rough page to take a look into. So let's just visualize this in small chunks, starting on that definition there. We're very interested in matrices that are diagonalizable. They have a lot of nice properties, building systems. This is something we'd like to be able to do, and being unable to diagonalize a matrix, if this came from an applied setting, sometimes has very severe consequences. If we can't diagonalize the matrix, right, in this particular format, we say the matrix is defective, and probably your model for the system you're building is defective as well at the same exact time. So it's pretty suggestive language. Diagonalizable is just a kind of factorization. We can factor A as some matrix P times a literal diagonal matrix D times P inverse. So this is the definition of what we mean by diagonalization. From the last section, we also would say A is similar to the diagonal matrix D, so it connects with the similarity transformation. But now we have a whole lot of stuff we can say once you've diagonalized the matrix. That matrix D right there in the middle contains, on its diagonal entries, the actual eigenvalues of the original matrix A. And in the matrix P, and the one with the inverse symbol on it, the columns are the corresponding eigenvectors at the same time, making that pretty nice if you have a diagonalization you're looking into. This is the last example we did right before the break. A has been diagonalized. Has been written as a matrix P times a diagonal matrix D times P inverse. Notice we just put an inverse symbol on it. We didn't actually invert it, but we know it's an invertible matrix. So the eigenvalues are automatically 5, 5, -2. So that's lambda 1 with multiplicity 2. Corresponding to that eigenvalue is eigenvectors v1, v2, the first two columns. Only because those eigenvalues corresponded to the first two columns of the diagonal matrix D. Then the third column, -2, that eigenvalue there corresponds to the third eigenvector v3, 2, 0, 1. So we have a one-to-one correspondence between entries on the main diagonal and the corresponding eigenvectors. And this is the really fast problem. If you're given this diagonalization, we essentially know everything about the eigensystem for A, all eigenvalues and associated eigenvectors. Well, that's the warm-up for the diagonalization theorem. Pretty much the rest of the notes is just focus on trying to diagonalize this matrix, thinking more about this theorem and the last theorem on the notes as well. Any questions or comments at all, folks, with this refresher problem? Okay, so if we had A and not the diagonalization, the questions now become, how do you in fact diagonalize A? And that's what's going on with example 3. It says, diagonalize this matrix or explain why it's not possible. We'll see some cases where it's impossible in these notes and some cases where we can go through the full process. But to start it off, it's always pretty much a 3-step process we do. And step 1 is just finding the eigenvalues. Really, this is a pretty good tour for all the real techniques and concepts in this entire section. Find the eigenvalues means we're going to look into the characteristic equation. So we take the determinant, A minus, we're usually using green for the eigenvalues, so let's keep that. Determinant A minus lambda I. Taking minus lambda I just operates on the meg diagonal. We'll subtract lambda from those two entries. So this turns into 2 minus lambda. 2, and then -3, -5 minus lambda. So it's written as a determinant, but this is now the characteristic polynomial set to 0, and it's the characteristic equation. It's a fast determinant. The main diagonal is 2 minus lambda times, let me try again on that, 2 minus lambda times -5 minus lambda minus the product of the off diagonal, 2 by 3 for a -6. So now let's work this out. So I'm kind of relaxing algebra in the middle of the process. I've got negative 10 minus 2 lambda plus 5 lambda plus lambda squared plus 6. So altogether, this is lambda squared plus 3 lambda minus 4. 3 and a negative 4 is nice because this tells us we have an immediate factorization of lambda, let's go plus 4 times lambda minus 1. So there's our fully factored characteristic polynomial. That small change, and now we're looking into the characteristic equation. And the zero product property of real numbers tells us automatically that we have eigenvalues. First one is from this factor, lambda 1. Is negative 4, and lambda 2 is positive 1. So that finishes out our first step, just getting the eigenvalues themselves. If this happened to have been a diagonal matrix, then this would have been pretty much an automatic statement, just saying what the entries are on the main diagonal for eigenvalues. That's a pretty good refresher already. This is essentially section 5.2 as a technique. Any questions at all getting eigenvalues? Okay, now once we have the eigenvalues, let's make a quick comment here before we jump into the next step. It says diagonalize the matrix or explain why it's not possible, but it is possible this time. If we have two distinct eigenvalues for a 2x2 matrix, we can automatically say A is diagonalizable. We'll get one eigenvector from this eigenvalue, linearly independent eigenvector from the second one. That will form the eigenbasis, just like we had a basis right here for the matrix P. So once we get those eigenvectors, we're building out P. And we already know how to build out the diagonal matrix D. It's just going to be 4, negative 1 as a 2x2 diagonal matrix. So let's make a quick comment that says two distinct eigenvalues. For a 2x2 matrix, this automatically implies A is diagonalizable. So that takes us now to step 2. We can proceed, find the eigenvectors, which means we have to solve two homogeneous systems of equations, one per each of the eigenvalues that we picked up. So let's organize this really carefully because we have to keep a correspondence between those eigenvalues and the eigenvectors we get. So when we put them all together, it's done in the correct order. So starting with lambda 1 equals negative 4. Sorry, my control Z is getting random there. Lambda 1 equals negative 4. The eigenspace is null A minus lambda I, which is null A, this will be a plus 4, I. We don't need to compute the whole entire null space, we just need a basis for it. And those basis vectors are going to be the eigenvectors we pick up. Probably just one, we'll get one eigenvector from each one of these. So we'll next solve. A plus 4i x equals a 0 vector. We drop this automatically into an augmented matrix. Going plus 4i means just adding 4 back to the main diagonal. So this will become 6, 2, negative 3, 1, augmented with 0, 0. Now we can say something for sure on this one. The null space is not trivial. The dimension is 1, which means there's got to be exactly one free variable in the system. And it doesn't look like it's too hard to find. The numbers are not the most convenient in this problem. We'll get a fraction out. But you could say divide row 1 by 2, or maybe even 6 to start. Let's divide by 6. We'll get 1, negative 1/2, 0. Now, if we multiply this new row 1 by negative 2, add it to that row 2, we would get 0 here. Multiplied by negative 2 will give us a negative 1 plus 1 for a 0 here. So automatically this row completely just goes away. And we have our free variable corresponding to the x2 variable. So here's x1, x2. We can now rewrite this as a system of linear equations. X1 equals positive 1/2. X2 is the free variable, so x2 is equal to 1 times x2. And now back over here, solving a plus 4i x equals 0, this implies x equals x2 times 1/2 and 1. So we have the full system solved here in parametric vector form. X2 is the parameter. It can take on any value whatsoever. Oh, sorry, I missed a chat. A -1 on, let's see, that was at 244. Sorry, I missed where the -1 comment was, Brian. The first one, so right here. Oh, yeah, that would have been a -1. Thanks for spotting that. So it should have been a -1 here. Thanks for the help with that in class and Brian on Zoom. And let me double check my 0 here. So I was multiplying. First, I divide this by 6. So I got 1, -3/2 for -1/2. Then I should have been multiplying this by a -2. So that would have been 0. That would have been a +1 minus 1 back to 0. So my arithmetic was wrong, but it just kind of equaled out with my expectation. I was expecting a free variable, so I knew it should have been 0. But it had to have been a -1 there. Thanks for spotting that, folks. So now back here, we essentially have the eigenvector. If you allow your eigenvector to be 1/2 and 1, that completely works. It's any vector here that's a multiple, but not a 0 multiple would work. Most often than not, though, people would do the following. Pick x2 equals either 1, it'll work out just fine, but the most convenient value would be a 2 to clear the denominators. This is what the back of the book would often do. You don't have to do it. Any eigenvector that's not 0, 0 is going to work. If we pick x2 equals 2, then we have for lambda1 equals -4, an eigenvector v1 equals 1, 2. So rescaling this by 2 just makes it slightly more convenient. If we had to do more things with this diagonalization, that would be a really good step to take. Well, we're halfway there. We need to find the other eigenvector corresponding to the other eigenvalue. Lambda2 is 1. But we're getting there. This is the process so far. So let's change gears and go to next lambda2 now equals +1. It has eigenspace. It's the null space of a minus 1 times I, 1 for the lambda. So if we solve the typical system for this, this is a plus 1 times I, x set equal to the 0 vector, where that's the eigenvalue. All we're now doing is adding 1 to the main diagonal. So this becomes 3, or hang on, a minus 1 times I. That's supposed to have been a minus. That was a bad copy error. So with that fix, a minus lambda I means minus 1 times I. This is subtracting 1 from the main diagonal. We get a 1, 2, and a -3, -6, augmented with 0, 0. And this one should be faster to solve. Just multiply row 1 by 2, add it to row 2. Multiply by -2. We'll get 0 here, 6 minus 6 for 0 here. So it's automatically row equivalent to 1, -3, 0. 0, 0, 0. And we're about ready to just read out the equations. This is x1, x2. Implies from this reduction, x1 equals 3x2. x2 is equal to 1 times x2. And we're essentially looking at our eigenvector right at that stage. It's going to be a 3, 1. So back to solving this system, we can say x equals, in parametric vector form, x2 times 3, 1. Set x2 to the most logical value, 1 will do the job. It can be anything other than 0 and still work out. But once we make that change, we have second pair of eigenvalues. Lambda 2 equals 1 corresponds to the next eigenvector, v2 equals 3, 1. So we're just about there. We have the complete eigensystem, all the eigenvalues, all the corresponding eigenvectors. Now we just put them all together and we can do a diagonalization of the original matrix A, which is just a fancy factorization. Well, any questions, folks, with the main work so far? Okay, so kind of a nice review problem in a certain sense because it goes over finding everything, eigenvalues and eigenvectors. And here's our big punchline to all this work. The third step is just to write out the diagonalization. So here it is. That original matrix A can now be factored as a matrix P, suggestively written in blue there, times a diagonal matrix D, times the first matrix inverted. So let's start with the eigenvalues. Lambda 1 was -4. And what's kind of interesting here is you might have called that your lambda 2. Just depends on how you factored, how you decide to go about the problem. Whether you put it in column 1 or in column 2 is irrelevant. You'll still get a correct diagonalization. So there's not a unique way to do this. There's often multiple ways depending on where you put your eigenvalues. The one thing that is critical is if you decide to put -4 in column 1, that means you have to go back to the associated eigenvector 1, 2. It has to also be in column 1. That's the only thing that has to be nailed down. It's the correspondence. So 1, 2 goes here. 1, 2 goes into the matrix on the far right. And then just move over to the next eigenvalue. This one is 1 on the main diagonal. Because we placed it in column 2, 3, 1 also goes in column 2. It'll go both here and here. Then finally, that's our full diagonalization. One comment I wrote in the homework is, to me, this is a great answer. I'm not going to ask you to invert the matrix, which gets extra painful if this was of size 3 by 3, for example. So whether you're doing this on a homework problem or on a final exam setting, this is a great stopping point. So let's just make a quick note. You do not need to compute this inverse. If we had to work more with this matrix, we might need to compute this inverse, but this is the main concept that we'd be tested on in a final exam setting. Well, any last questions at all, folks, with our first diagonalization? Okay, so kind of a strange number game, putting all these weird pieces together like null spaces. We're thinking about the dimensions of these null spaces as well to even know if we have diagonalization. And these values right here, because the inverse definitely exists, forms an eigenvector basis for R2. So this is just a particular nice basis for that space. So let's try this out again. If we can do it once, we should be able to do it again. It says, well, this one's a little bit different of a problem. It says diagonalization is the first major concept about square matrices, n by n ones, that do not fit into the invertible matrix theorem. And it says explain why using the given matrix A below. So that's a kind of a strong statement because it seems like every new concept we've been looking into, say eigenvalues for one, fits right into the invertible matrix theorem. But this example is telling us diagonalization is now at that one spot where it doesn't actually fit with invertible matrix theorem. First, let's think about this matrix A. This one was diagonalizable. And if we look at the original matrix, if you took the determinant, that would be -10 plus 6. It's non-zero. A is invertible, and it's also diagonalizable. Let's take a look at this one next. We can think about, well, explain why diagonalization doesn't fit into the vertible matrix theorem. Well, let's just think about first, is this matrix even invertible? Well, if you have a zero row, you could do a determinant that goes across row one. Determinant is 0, and it tells us A inverse does not exist. Or we can analyze this in a totally different kind of way. This matrix is lower triangular. That means the eigenvalues are on the main diagonal, here, here, and here. So we can say A has eigenvalues lambda 1 is 0, lambda 2 is 4, and lambda 3 is 2. So that tells us a lot of information altogether. First, lambda 1 is 0 being an eigenvalue. That's the part of the invertible matrix theorem we were looking into. If it's not an eigenvalue, A inverse exists, connecting part A all the way down to part S. But it is an eigenvalue in this case, so that tells us part A is false. A is not invertible. So let's write out that piece right there. Since lambda equals 0 is an eigenvalue, A inverse does not exist. A is not invertible, in other words. And using the same comment we made from before on our original matrix A from here, if you have two distinct eigenvalues on if you have three distinct eigenvalues on a 3x3 matrix, you will get three eigenvectors. And those eigenvectors are automatically linearly independent. That gives you diagonalization. So we can now say, since A has three distinct, they're all different values, none of them has repeated or higher than one multiplicity, three distinct eigenvalues, and A is 3x3, we have that A is diagonalizable. So that's kind of unfortunate in a certain sense. A is diagonalizable, but A inverse did not exist. And the last problem, A was diagonalizable and A inverse did exist. Because of the way this is working, it looks like A inverse existing or not has nothing to do about diagonalization in this problem. So this shows diagonalization does not fit into the invertible matrix theorem. So, well, I mean, it's good in a way. It means our invertible matrix theorem didn't get bigger. And it also means we have to work a little bit harder when it comes to concepts about diagonalization, because for something that doesn't fit in the invertible matrix theorem, you've lost all of this leverage right here. But that's kind of nice to know we're looking into something new, something that does not fit into that long statement of ideas, which are equivalent. Any questions at all, folks, with example 4? Okay, well, this one is diagonalizable. It didn't ask us to diagonalize it. But we'll take a look into a couple more problems just along those lines. It says diagonalize the matrix A, just like our first A problem that we did today, or explain why it's not possible. It's another lower triangular matrix, so we're not going to work too hard on step 1, finding the eigenvalues. We can just state them. On the main diagonal, for the lower diagonal matrix, we have eigenvalues. Lambda 1 equals 2, and lambda 2 equals 4. But these eigenvalues are not equal in a certain sense. This one is repeated. It shows up twice on the main diagonal. So lambda 1 equals 2 has multiplicity 2. The one below, just to fill this out, has multiplicity 1. I'll just write multi for multiplicity. As multiplicity 1, and the sum of the multiplicities is always the size of the matrix, 3 for the 3 by 3. But the multiplicity 2 is now where all the diagonalization is really going to hinge upon. The dimension of that eigenspace could either be 2 or it could be 1. The dimension of the eigenspace can never exceed this multiplicity, but it can dip below. So we have an important concept that's going to tell us A is diagonalizable if and only if the dimension of the null space of A minus, let's look into the higher multiplicity eigenvalue, A minus 2 times I, is exactly 2. We need that dimension to be 2 because diagonalizing means we have to have an eigenbasis with enough eigenvectors. This one was 2 by 2, so we needed 2 linearly independent eigenvectors. The dimension is the number of eigenvectors in the basis. For a 3 by 3 matrix, we'll get 1 linearly dependent eigenvector here, and we require 2 more to fill out and actually get an eigenbasis. So if that dimension dips to 1, we'll know immediately this whole system is not diagonalizable any longer. So that means it's really a good idea to not focus on the lower multiplicities first. Look into the higher ones first, because that's where the whole problem is going to hinge on. Well, any questions, folks, before we look into this dimension right here? Okay, it's been a long time since we thought about that dimension. So just for a quick refresher problem, here's how we thought about these kind of dimensions way back in section 4.5. Whether you're looking into a matrix like this one, 4 by 7 or a 5 by 7 kind of matrix, the big theorem that helps us out that tells us it is the dimension of a null space, whether it's null A or null A minus 2i, any null space, is going to be the number of free variables in the homogeneous equation. So if we use this theorem right here, we may not have to do a whole lot of work whatsoever. We'll analyze what this system looks like. Null A minus 2i just means we're looking into the solution set for A minus 2 times I, x set to the 0 vector. We can drop immediately to the augmented matrix. Minus 2i means subtracting 2 on this main diagonal. So we're going to get 0, 0, 1 on column 1, 0, 2, 0 on column 2, and 0, 0, 0 on column 3. Let's put this in echelon form. In echelon form, I've got a 1, 0, 0, 0, 0, 2, 0, 0, and all zeros on the last. We have variables x1, x2, x3. But this system has 2 pivots. That means there's exactly 1 free variable for a minus 2i x equals 0, but we required 2 free variables to get the dimension to come out to a 2. So even if we went further, we're only getting 1 eigenvector out of this. There's only 1 parameter, x3, for dimension 1. So here's where the problem should really stop. We can say 1 free variable, it's x3. This implies the dimension of the null space of a minus 2i is exactly 1. So here's that theorem working really hard for us. It wasn't equal to 2, so we can conclude immediately, therefore, A is not diagonalizable. Or a nice way to say this, abbreviated, is i.e. A is defective. So that's kind of a nice problem in a way. The defective matrices just means try to find the point at which it could become defective, analyze the dimension of that null space, and your work is done if the dimension is lower than the multiplicity. So that's a fun way to do the problem. If the dimension came out to 2, however, we'd have to proceed through all of the rest of the steps, get those eigenvectors, and then do the final diagonalization. Well, any last questions, folks, on finishing example 5? Okay, again, these are basically like final exam review questions when you think about it. We're looking into null spaces, we're solving homogeneous systems, we're thinking about dimension at the same time as the number of free variables as it relates to null space. So really it's just one big review at this point in section 5.3. Let's do this all over again for the sake of practice. Almost the same kind of problem that we're looking into, but just slightly different numbers below the main diagonal. We'll diagonalize this if possible, or explain why it's not possible. And we have the same eigenvalues, 2, 4, 2. So let's start there. We have lambda 1 is 2 with multiplicity 2. And we have lambda 2 is 4 with multiplicity 1. Using the last problem as a model, we know we should investigate the higher multiplicity first, see what the dimension of that eigenspace is. We get 2 free variables. That's 2 linearly independent eigenvectors. And the third will come from the eigenspace on lambda 2. So that will make it diagonalizable. So let's look into the eigenspace for lambda 1 equals 2. This has eigenspace null A minus 2 times I. When we're looking into that null space, just means we're solving A minus 2 times I times X equals 0. But the punchline is you just subtract 2 from the main diagonal and start row reducing. So this will become, let me get that out of there, 0, negative 1, negative 3, 0, 2, 0, 2, 6 rather, and 0, 0, 0. We have the 0 vector augmented in because we're looking into a null space. And let's see, we can row reduce by multiplying that row by negative 1, promoting it into row 1. So we'd have a 1, negative 2, 0, 0. Row 1, we can just drop down into row 3. So we have a zeroed out to row 3. And we can take this entire row right here, multiply it by, say, a positive 3. Add it to the old row 3, replacing it into row 2. That'll give us a 3 minus 3 for a 0 on this entry. Multiply by 3, so it's a negative 6 plus 6 for a 0 on this entry. And the rest are going to be zeros. So the row reduction is complete right at that step. And notice there are 2 free variables this time, so the dimension of this null space is actually 2. Let's write that in as just a side comment to connect our ideas from the last example. There are 2 free variables. Which then means the dimension of the null space of A minus 2I equals to A is of size 3 by 3. So we'll have a third eigenvector from that eigenvalue. This tells us automatically A is diagonalizable, which means we have a whole bunch of other steps we have to get through, but we can complete this problem. Here's x1, x2, x3. The next step is just to write out the system of equations. So we have x1 is 2x2 and 0x3. Then x2 is a free variable. We'll write x2 is 1 times x2. x3 is also free, so it's equal to 1 times x3. So the solution, or the vectors x inside that null space, will have the form x equals x2. We're just rewriting this solution set in parametric vector form now. Coefficients of x2 go 2, 1, 0, plus x3. x3 coefficients go 0, 0, 1. So that's our parametric vector form. Essentially, this is the null space. If we wrote it out as a span, it'd be directly equal to this. But if we set x2, 1, x3, 0, we get one eigenvector, 2, 1, 0. And if we do the vice versa, set x2 to 0, x3 to 1, we get the second eigenvector, 0, 0, 1. So those are our next eigenvectors that we can pick up. So to paraphrase, lambda 1 equals 2 corresponds to two eigenvectors, v1, 2, 1, 0, and v2 equals 0, 0, 1. So those are the first two columns for the diagonalization we're going to get on A. It's a long process, so we're halfway there. We're done with this eigenvalue. We move over to the next and essentially repeat these steps. Any questions at all, folks, with this block of work right here? Okay, so let's write out this next step. We're moving to the next eigenvalue, so just to organize, I'm going to write, we're now on lambda 2 equals 4. This has eigenspace. You don't necessarily have to write it has this eigenspace, but I found it's a good way to kind of just organize your thoughts on what you're about to do next. Because if I write a minus 4i at some point, it reminds me I'm coming back here, augmenting with the zero vector, and subtracting 4 from the main diagonal. So same steps as before, they're new augmented matrix this time, subtracting 4 on those main diagonal entries gives us -2, -1, -3, then 0, 0, 6, then 0, 0, -2, augmented with the zero vector because we're looking into a null space. So we need to row reduce this thing. Loads of ways to do this one. I'd probably maybe work off this one right here. Let's multiply that row 2 by -1, making it a 1, 0, 0, 0. Then once it's a 1, 0, 0, it's going to wipe out that entry right here. You can multiply this by 2, add it to row 1. Now it's a zeroed out row. You could just take that 0 row and put it on the last row down here, 0, 0, 0. So all that's left is -3, 6, 2. But you can wipe out the -3 once you have a pivot here with zeros to the right. It's just eliminating these things here, above and below rather. So multiply this by 3, add it to this, when you get a 0, 6, -2. And then we can just shuffle it into row 2 right here. So we have 0, 6, -2, 0. Still not in row reduced echelon form. We'd want to divide this by 6 to get it there. So one last step. We have 1, 0, 0, 0, 0, 1, -1/3 when dividing this by 6, 0, and then everything else is zeroed out. As a check on this, we should have dimension 1 on this null space. The dimensions have to total to 3 when it's diagonalizable. That means there should just be one free variable like we're seeing in this system. That free variable is x3. So now finally, writing out the system of equations, row 1 is just saying x1 is 0. So that's exciting. Next row is saying x2 is +1/3 times x3. x3 is the free variable, so you could write x3 as 1 times x3. And now we can write down the description x for all vectors inside this null space. So X is going to be just one parameter, X3 times 0, 1/3, 1. And that's a totally fine eigenvector, but it might be confusing if you are checking the solutions for the odd exercises. Oftentimes, like we mentioned on the other problem, the book likes to set X3 equal to 3, the least common denominator, to just clear out those denominators. Setting X3 to that value is going to give us this eigenpair. We have lambda 2 is 4. Eigenvector V3 now, kind of confusing with the subscripts. We're setting this to 3 and just multiplying it out. So the rescaled eigenvector is 0, 1, and 3. So we're about there. We just need to write down the diagonalization. Essentially, all we've done is redone these entire steps in this block for just the new eigenvalue. So lots of practice doing that. Any last questions before we go to the punchline, the diagonalization itself? Okay, so here's the full diagonalization. We can say the matrix A, let me start with the matrix A. It can now be factored in this particular way. There's lots of different ways to write down this particular diagonalization, because notice it depends on what you picked for your eigenvector in the very first place. You've infinitely made choices. You could have picked 4, 2, 0 as your first eigenvector right here, for an example. So if you see things that look a little bit weird in the back of the book, it might be because of stuff like this, picking a particular value of a parameter. Let's start with the diagonal matrix and the repeated eigenvalue. For lambda 1 equals 2, we'll place it here on that main diagonal and here, which means we have to place these eigenvectors in any order you'd like. But which order you pick, you have to duplicate on the inverted matrix as on this matrix here. So if you want to get fancy, you could go 0, 0, 1. Just make sure you start with 0, 0, 1 on this one. I think it's just a little bit easier to go in order as we wrote them. There's no reason to mix things up further. So let's go 2, 1, 0 and 0, 0, 1. Last eigenvalue is 4, so it'll go over here, 0, 0, 4, last position on the main diagonal. That means V3 has to be in column 3, so 0, 1, 3. Same comment as before, you don't have to invert the 3 by 3 matrix. This would be an excellent stopping point, whether it's a homework problem or an exam setting. So lots of work when it is diagonalizable, unfortunately. That's why it sometimes pays to look into higher dimensions or higher multiplicities like this one to test right away if you can even go further to the next steps. But any last questions, folks, on the full 3 by 3 diagonalization? Okay, well, we're nearly done with these notes, nearly done with chapter 5. All I have left is a couple theorems and a couple concepts to look into as it relates to diagonalization. For example, theorem 6 we've used repeatedly already in these notes, and it's an official theorem. If you have an n by n matrix with n distinct eigenvalues, it is automatically a diagonalizable matrix. So this one kind of feels like a repeat of what we did on, I think that was example 4. But just as a reminder on how it would go to do this problem, this one is an upper triangular matrix, so we can say the eigenvalues are lambda 1 equals 0, lambda 2 equals 1, lambda 3 equals -1, all are distinct. So this implies A is diagonalizable. And again, it's kind of a deja vu problem. I probably should have not doubled up on the same kind of problem, but quick review, I guess. The other question was about invertibility. And if you just did, say, an observation, this tells us A is not invertible like we did earlier, or maybe a determinant this time, that'd be a great way to analyze it. Either way we look at this, it's not invertible. We could say since determinant A is 0, cofactor expansion down column 1 just produces 3 zeros multiplying the submatrices, subdeterminants. So we have a determinant 0. A is not invertible. And yet it is diagonalizable. So this is kind of a dangerous question in a certain sense. Notice the difference between diagonalize the matrix A if possible versus a question that's just simply asking, is A diagonalizable? You could have answered, is A diagonalizable, by doing all of this, by encourage you use a theorem if this comes up as a homework question or exam question, because if I don't specifically ask you to diagonalize, you're never meant to do all this stuff like you saw here. So that's a great theorem. So it's our second look into this kind of same concept, but finally with an official theorem supporting the work. We made other comments along the way on these notes that the next theorem is going to finally make concrete as well. So here's the next big idea, the last section of these notes. It's kind of a beast of a theorem. It's 3 different parts. Part B has 2 subparts, but it's just one nice way to encapsulate really everything we've been saying about eigenvalues, eigenvectors in one big spot. So theorem 7 is a big rundown theorem, says we're looking into n by n matrices. So eigenvalues is a concept we can ask about. Let's say the distinct eigenvalues are lambda 1 through lambda p. When we say lambda 1 all the way through lambda p, we're also mentioning implicitly that p is less than or equal to n, where the n came from here, the size of the square matrix, n by n. So there could either be n distinct eigenvalues, or there could be slightly fewer, so some of them will have higher multiplicities. So one big concept already is for every value k, every one of these eigenvalues, so pick a subscript k, the dimension of the eigenspace, we've used this concept once before, is less than or equal to the multiplicity of that eigenvalue. So that's a useful concept in its own. That tells us the sum of the dimensions of the eigenspaces are not exactly n. When it does come out as n, it's diagonalizable. And when it's not, that's when we have a defective matrix. But just tying this back to section 5.2, here we were looking into this theorem for n by n matrix. We mentioned through the fundamental theorem of algebra, there will be exactly n eigenvalues, which means this makes this feel weird. This is just mentioning the distinct eigenvalues. If we count them according to their multiplicities, they'll be exactly n. And so the concept that ties in with this is the sum of the multiplicities of your eigenvalues is always n. If we add up all the repeats of your eigenvalues, but the dimensions of the eigenspaces may or may not be n whatsoever. So that's part A, just putting on paper comments that we've been making quite a bit already in these notes. Part B we've used as a concept as well. A matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces does in fact equal n. So when that happens, we can diagonalize the matrix. And below are just conditions where this happens. It can factor completely into linear factors, and the dimension of the eigenspace lambda k equals the multiplicity of lambda k for every one of the eigenvalues. So we saw this in one of the examples. Let's take a quick tour just as a refresher. Here we had multiplicity 2 for lambda 1, but 2 free variables meant the dimension was also 2 for this eigenspace. That's why this one was diagonalizable. And the problem above it, somewhere, this is where it went wrong. The multiplicity for this eigenvalue was 2, but we saw that the dimension of the eigenspace was just a mere 1 on this one, and that's what made it non-diagonalizable. So that's all this part 2 right here is trying to convey. Diagonalizable means dimension always equals the multiplicity for every single eigenvalue. And part C is just a reminder of the eigenvectors we get. They're going to be linearly independent and they form a basis. I'd say really the pretty interesting part of this whole theorem is right about here. This is where the last questions in the notes kind of mangled that. This is where the last questions in the notes ties back to. And it's a great concept to think about diagonalization. That has to work out an equality for the dimension and the corresponding multiplicity of the eigenvalue. So it's a lot of statements taken all together. We'll focus on this part 2 on the next 2 examples. Any last questions or comments, folks, looking into this pretty big theorem? Okay, let's put it into practice. So quick way to use this theorem is a couple concept questions. There'll be some similar questions in the homework as well. Just give you these random scenarios. A is a 4x4 matrix. 4 is the n that we see up here in this theorem. We're told it has 3 distinct eigenvalues in this problem. So we have a lambda 1, a lambda 2, and a lambda 3. We're also told one of those eigenspaces has dimension 2. That's kind of nice. If one of them has dimension 2, we can say dimension null a minus, let's say it's lambda 1 that has that dimension. We can just rename these if it was a different lambda. That dimension is 2. We want to now know is if A is diagonalizable. Well, that's going to happen if the dimensions of the eigenspace equals the multiplicity for every single one of these eigenvalues. If the dimension of the null space is 2, well, the dimension is less than or equal to the multiplicity of that eigenvalue. So that tells us this eigenvalue, lambda 1, has multiplicity. Let's think about it. Well, if the dimension null space is 2, then that can't give us a multiplicity of 1, because this is always the eigenspace dimension less than or equal to the multiplicity of the corresponding eigenvalue. So this can't dip below that dimension. It could be a 2. That'd be a nice case. And what about 3? That works with this part A right here, if the dimension was 3, because the dimension of the eigenspace is lower. But then you have a problem here, because these multiplicities are at least 1, and the total of the multiplicities has to come out to the size of the matrix 4. So if you bump this up to multiplicity 3, it's too big, because these are at least multiplicities 1, and that would come out to a 5. So this has to have multiplicity 2 specifically. It can't drop down to a 1. It can't go up to a 3. Looking at lambda 2, what's this multiplicity? Well, it can't be a 2 any longer, because if it was a 2, we'd be up to a total multiplicity of 5. This has to have multiplicity 1, and by the similar reasoning, lambda 3 also has to have multiplicity 1. Then this part takes an effect. The dimension of the eigenspaces has to be less than or equal to these values 1, but they can't be dimension 0, because if the eigenspace was dimension 0, the only thing inside that null space is the 0 vector, but 0 as a vector is not an eigenvector at all whatsoever. There is an eigenvector corresponding to lambda 2, or else it wouldn't have been an eigenvalue in the very first place. So once these come out to dimension 1, it means dimension null a minus lambda 2I is also 1. Dimension of null a minus lambda 3I has to also be 1. And so the sum of the dimensions of this eigenspace comes out as dimension 4 in its sum. That's what we were gunning for. This part that's underlined says, if for every eigenvalue, we have the dimension of the eigenspace is the same, we have diagonalizable. So we can say, therefore, A is diagonalizable. So another way to think about it is the sum of the dimensions of the eigenspaces. I guess that's just as important. Let's put this in purple as well as another main takeaway. The sum of the dimensions of the eigenspace was equal to the n value for in this problem. And that's another great way to look at it. Either this line or this line are both lines telling us A has to be diagonalizable in this problem. So if you know something about the dimension and the number of eigenvalues, you can determine diagonalizable without even knowing what the matrix A was in the very first place. So really, it's all about just thinking about these concepts in Theorem 7 is what examples 8 and 9 are about. We'll try it one more time, but any questions with this so far? Okay, let's try it out again. New matrix A, this time it's 5 by 5, but only 3 distinct eigenvalues. Scroll a little bit on this one. So if we have 3 distinct eigenvalues, we have a lambda 1, don't know why I wrote an equals, I'm thinking the multiplicity. Let's see if we can fill this information in. A lambda 2, we'll think about the multiplicities on every one of these. But those are the eigenvalues. We're told that one eigenspace is two-dimensional. Another eigenspace is one-dimensional. Without a loss of generality, we can say lambda 1 is the two-dimensional, lambda 2 is the one-dimensional. If that were wrong, we can just rename these to make it true. So let's say, for example, dimension null A minus lambda 1 I. That eigenspace, let's make this the two-dimensional one. Dimension null A minus lambda 2I. This is the one that's one-dimensional. So the only thing that's not filled in is dimension null. Let me fill in the blank on this. That's supposed to be an A minus lambda 3I. This is the one that's not clarified. As far as the multiplicities go on this, it's pretty large. It's of size 5 by 5. If the dimension of this null space is 2, that means the multiplicity is bigger than or equal to 2 on this one. This one has dimension 1. This multiplicity is bigger than or equal to 1. It could be dead on equal. It just can't be less than 2 on this one. The question is it possible that A is not diagonalizable? Is there a way that this particular system could work out for something non-diagonalizable? Well, first let's put down, if this is a 5 by 5 matrix, and we have that these are 1 and 2s, well, the multiplicity on this one is going to be bigger than or equal to 2 as well. It has to sum up to 5 in total. But over here, the dimension of the null space doesn't have to be 2. It's possible that this dimension could be a 1. If it's a 2, that the sum of the dimensions would be equal to 5 altogether. So because this is a what if kind of problem, let's say, what if the dimension is 1? We weren't told that, but that's possible in some systems. If the dimension is 1, the sum of the spaces dimensions are 4, which is less than the size of the matrix as a 5 by 5. And this means it's not diagonalizable. So it is all determined by what happens right exactly here. So it's kind of an odd question asking, is it possible? And we can say, yes, it is. Yes, if dimension null A minus lambda 3I is 1 instead of a 2, then the sum of dimensions is not 5, And so A is not diagonalizable. Again, weird question because it's also possible it is a 2. In that case, the dimension would be 5, and it would be diagonalizable. Well, that's the conclusion of diagonalization in this section. Any last questions or comments at all, folks, about any of the work we've done in these notes so far? Okay, well, we've got about 9 minutes. Let's see what we can do in that amount of time. Our work in chapter 5 is now concluded. If you're interested in some applications to eigenvalues, I have some kind of heavy calculus 3 kind of applications that I listed here. And for chapter 6, I don't think we can make a lot of segue into chapter 6 with our limited amount of time. Let's take a look into what we're getting into. Maybe we'll do a couple quick problems and then come back on it a little bit more fresh when it's Thursday. The major idea with this section is now we're looking into geometry of the vector spaces themselves. And the biggest tool that gives us that geometry is the dot product. When we've actually done a dot product before, way back in chapter 2 when we were doing matrix multiplication. Dot product just tells us if you take u dot v, all you're really computing is u transpose times v, and this is the result you get. You just multiply the corresponding entries, u1 times v1 plus u2 times v2. Hang on, that's a u. I don't think I've ever noticed that before. Sorry for that random correction there. And so on, un times vn. So multiplying the corresponding entries gives you that object. It just seems like a weird numerical game, but the dot product turns out to be absolutely vital to geometry of these vector spaces. Because once you have the dot product, you have the idea of the norm of a vector or the length of a vector. So the length of the vector is the square root of v dot v. And the reason this is so critical is once you have the length of a vector, you can now do calculus on these vector spaces, whether it's R2, Rn, and so on. The reason calculus requires length is because think way back in the day when you wrote something like limit as x goes to a of f of x equals L. There's really a norm working in the background for this as well. It's just we were in R, not R2 or R3. And so we used absolute values to make this work. We said that this limit only makes sense if for every epsilon bigger than 0, there exists a delta bigger than 0 such that if the norm or the length of x minus a, the distance from x to a, or just the absolute value of x minus a, is less than delta, that implies the norm of f of x minus L is less than epsilon. We'd love to be able to reuse all this stuff, and this is what makes it work. Instead of writing absolute value for an R2 or R3, we just say the norm. We'll look into the length of two different vectors, and it gets even more crazy because once you have the distance, the norm of the length of u minus v, you can define a norm in other weird spaces like C01, the space of continuous functions on closed domain 0 to 1. There's lots of interesting norms. One of them is, say, the supremum of the function, the maximum value it obtains on 0 to 1, and 1 exists. Then once you have a norm, we're going to look into angles between vectors like in R2, R3, but you can also ask and answer the question, what is the angles between vectors in a space of continuous functions? You can answer this question, a wild-looking question. What is the angle between e to the power t and t cubed? Once you have the right norm, which comes from the right dot product in this space, you can redo all this kind of work. That's where all these notes are trying to get to. We're going to majorly work into the angle between the vectors, focusing on when they're orthogonal and when they're not. So that's kind of the rundown of what we're doing in these notes so far. Any questions or comments about these ideas at the moment? Let's do maybe one problem since we've talked through a little bit at a time. Let's do u dot v and u dot v times v. First one's the dot product when we see a u dot v here. And these are pretty fast to compute, but just to tie together the notes and matrix multiplication, it's formally defined as u transpose times v. U transpose is 3, 4. V is 2, -3. And thinking back in terms of matrix multiplication, let's see if this even makes sense. This is a 1 by 2 matrix. This one's a 2 by 1. Inner dimensions match, so you can multiply this. Outer dimensions 1 by 1 tell us the result is a scalar. That's kind of a weird multiplication. We're taking vectors from R2, multiply them in a non-standard way. That's why we like to emphasize the dot sometimes in the dot product, sometimes called the inner product with brackets, because this is a very, very non-standard multiplication. Result we get, using ordinary process in matrix multiplication, is 3 times 2 for a 6, plus 4 times -3 for a -12. So the dot product is -6 on this one. And this is now a strange amalgamation of symbols. The parentheses are required here so that we can think in the right terms of order of operations. This is just scalar multiplication. So this is our new vector by a vector multiplication. There's other kinds of products like cross products, but we'll focus primarily on the dot product. And this one, u dot v times v, is just a scalar multiplication. So u dot v times v just means take the result of the dot product, -6, rescale v to -3, and we get to -12, +18. And example 1 is done. In all honesty, section 6.1 is kind of a fun section. There's nothing too crazy we're doing on this. Some of the results we're doing go pretty fast. So it's kind of a get everyone on the same sort of page with the new operators, the inner product, length, and distance before moving on to the next section, 6.2, 6.3. Any questions at all, folks, with the dot product at the moment? Okay, and if you're curious, sometimes the dot product u dot v, if you've seen this in a different context, is written this way, u comma v. When it's written this way, it's often called an inner product. Just depending on the book, sometimes the dot product, the actual dot is emphasized. Other times in this bracket notation, the inner product is what's emphasized. But we'll come back to these notes when we're back on Thursday. 6.1 is kind of short, so we may start 6.2 as well. Looks like 6.2 will probably be our last section of the entire semester. Any last questions at all, folks, before we call it a day? Okay, well, have a great afternoon, folks. We'll be back to it on Thursday.